Welcome, everyone, to today's Explainer. We spend so much time talking about things like data throughput, fiber optics, and cloud storage, but today we're taking a look inside those massive, highly secure facilities to talk about the invisible, constant enemy of the internet: heat. Every single digital transaction generates heat, and figuring out how data centers deal with these massive thermal loads is honestly one of the most fascinating engineering challenges of our time.
So here is our quick roadmap for today's Explainer. We're going to start with the data center heat problem. Then we'll break down how air cooling works, followed by how water cooling works. After that, we'll dive into the great cooling trade-off, and finally wrap up with how facilities are making the right choice.
All right, let's jump right into Section 1, the data center heat problem.
Picture this. Literally thousands of high-powered computers crammed into one massive room. The servers, the processors, the storage devices, the network equipment, they all have this one thing in common. They generate massive, almost incomprehensible amounts of heat every single second they're running. It's just a relentless byproduct of computing power.
So what happens if we don't get rid of that heat fast enough? Well, it's not pretty. Equipment temperatures spike almost instantly. And to protect themselves, systems will throttle their performance, which means your data slows down to a crawl. Alarms start triggering across the facility, and ultimately, critical operations can just fail entirely. That's exactly why cooling systems are, for sure, the most critical part of any data center's infrastructure. Without cooling, the internet literally just stops.
Now, as you can see here, the fundamental difference between our two primary cooling systems really comes down to one core concept: how the heat is ultimately rejected outdoors. In an air-cooled system, the heat is rejected directly into the outdoor air. In a water-cooled system, that heat gets transferred through a water loop and is usually rejected through evaporation. They both do a fantastic job, but they go about it in completely different ways.
Moving right along to Section 2, how air cooling works. Let's see exactly how this first solution tackles that continuous heat load.
Okay, so the journey of heat removal in an air-cooled setup is fairly straightforward. First, the cooling system pulls the heat right out of the server room. A super common piece of equipment for this is an air-cooled chiller. This chiller produces chilled water that cycles to the indoor cooling units. But here's the magic mechanism. Instead of using a complex cooling tower outside, large condenser fans just blow outdoor air directly across coils to reject that heat into the atmosphere. Actually, I should also mention that some smaller data centers might bypass the chilled water entirely. They use direct expansion, or DX systems, where a refrigerant just absorbs heat from the room and transfers it straight to an outdoor condenser.
Let's weigh the pros and cons here. On the plus side, air cooling is so much simpler. You don't need elaborate cooling towers or condenser water pumps. And the biggest win? They use little to no water for heat rejection. That means you completely avoid the strict water treatment requirements that come with other systems. This makes air cooling a huge win for smaller edge facilities, quick retrofits, or places experiencing droughts where water is heavily regulated. But, there's always a catch. They are generally less energy efficient. As outdoor temperatures rise in hot climates, the equipment has to work incredibly hard to push heat into an already hot environment. That shoots electrical consumption way up and drops your overall cooling efficiency.
Which brings us to Section 3, how water cooling works. Let's explore the mechanics behind these more complex but highly efficient central plants.
Now, the water cooling journey is a bit more involved. It's kind of like a multi-stage relay race of heat transfer. First, just like before, indoor cooling units pull heat from the server room and chilled water carries it back to the chiller. But step 2 is where things pivot. The chiller transfers the heat to a completely separate condenser water loop. Then, in step 3, this condenser water travels outside to a cooling tower. Finally, the heat gets removed from the whole system through the incredibly powerful process of evaporation.
And this right here brilliantly illustrates why the massive hyperscale data centers almost always go with water cooling. The major advantage? Unbeatable energy efficiency. Water is just fundamentally better at transferring heat than air is. Because it can move large amounts of heat so effectively, these systems are absolutely perfect for high-density environments. Plus, in cooler weather, you can run economizers, basically using the cooling towers to partially replace mechanical refrigeration, which boosts efficiency even higher. But the downsides are pretty serious. These systems are highly complex to maintain. They require massive amounts of water consumption because of that evaporation process, and the water quality is absolutely critical. Poor water treatment can lead to scaling, corrosion, and fouling, which means you need constant, strict monitoring. All right, moving into Section 4, the great cooling trade-off. Because neither of these systems is perfect, modern data centers are locked in a constant tug-of-war.
To really grasp this trade-off, we got to look at two vital metrics. First up is PUE, or Power Usage Effectiveness. This metric measures the overall energy efficiency of a data center. Because water transfers heat so much more effectively than air, a water-cooled system is generally going to give you a significantly better PUE. It just uses less electrical power to get the cooling job done.
But wait, then we have WEE, or Water Usage Effectiveness, which measures the facility's water consumption. And herein lies the ultimate dilemma. An air-cooled system might have a worse PUE because it burns more electricity, but it boasts an excellent WEE because it conserves water. Meanwhile, a water-cooled system saves electricity but has to evaporate massive amounts of water to pull it off. So what do? Save water but burn electricity, or save electricity but consume vast amounts of water? Facility owners are forced to constantly balance the two.
Okay, really quick. Before we talk about how they actually make this choice, I want to bust a major myth here. When we say air-cooled or water-cooled, it does not mean the servers themselves are being blasted with outdoor wind or that water is flowing directly over the computer chips. No way. Many air-cooled data centers still use a closed loop of chilled water entirely inside the building. It's just that the heat is eventually pushed to the outdoor air. And conversely, many water-cooled data centers still cool the actual server room using indoor air handling units. The water part mainly refers to the central plant transporting and rejecting that heat out via the cooling towers.
Let's wrap it all up in Section 5, Making the Right Choice. Let's figure out how facilities finally make the call on their infrastructure. So, the crucial takeaway here is that there is absolutely no universal best system. The final decision depends heavily on a bunch of local factors. What's the local climate like? How do utility costs for electricity compare to water? How available is the local water supply to begin with? What's the rack density? And what are the company's long-term sustainability goals? So, for example, a data center built in a desert or drought-prone region is almost certainly going to favor an air-cooled system to protect the local water supply, even if it costs them more on their electric bill. On the flip side, a massive hyperscale facility up in a cooler climate with abundant water, they'll likely choose a water-cooled system because the long-term energy savings are just way too significant to ignore.
And look, the stakes are literally only getting higher. The future of data centers is rapidly heating up. With the massive explosion of AI and GPU-heavy workloads, the sheer amount of computing power packed into a single rack is driving unprecedented heat densities. Air and traditional water plants are having to work harder than ever before. In fact, to keep up, the industry is already moving toward advanced liquid cooling technologies like direct-to-chip cooling and full immersion cooling, where liquid finally does get up close and personal with the electronics.
But through it all, the fundamental goal never changes. We have to move heat away from those servers as efficiently, reliably, and safely as possible, which leaves us with one massive critical question for the future of our digital infrastructure. As AI and massive GPU workloads push our current cooling systems to their absolute limits, how will the data centers of tomorrow balance that ultimate trade-off between power efficiency and water conservation? It is a challenge that is absolutely going to define the next decade of the internet. Thank you so much for joining me for this explainer. I hope this really helped demystify the incredible invisible engineering that keeps our digital world from melting down.